Hi everyone and welcome back. Last lesson we left off at applying the first principle to a wide range of functions to find their derivatives. This process of finding the derivative is honestly super long, and there is a shortcut that we can establish so we can find it quicker. So if you remember from last lesson, we found that the derivative of x squared is equal to 2x, and the derivative of x cubed was equal to 3x squared. Now we can keep going, and we should find what the derivative of x to the power 4 is, so we can maybe establish a pattern if we see a trend. So we can do this by just using first principles. Limit of h approaches 0 of f of x plus h minus f of x all over h. And now subbing in our function, we get x plus h to the power 4 minus x to the power 4 over h. Now this expansion is quite long, so I am going to skip a step in between because I just want to get to the answer quicker, but you can, at home, you can go through and expand it fully if you're unsure of the answer. Oops. So if you expand here, you should get this: x power 4 plus 4x cubed h plus 6x squared h squared plus 4xh cubed plus h to the power 4 minus x to the power 4 all over h. This is something called a binomial expansion, and you'll learn about it eventually. Basically, it allows you to find and expand stuff that has large powers. So if we just simplify this, the x to the power 4's cancel out, and you're left with 4x squared h plus 6x squared h squared plus 4xh cubed plus h to the power 4 all over h. Now we see that every single term up here has an h, so we can divide h from top and bottom, and we're left with 4x squared plus 6x squared h plus 4xh cubed plus h to the power 3. Now applying the limit, every single one of these terms will become 0 because h is approaching 0, and we're left with 4x power 3. Since this becomes 0, this becomes 0, this becomes 0, we just have 4x power 3 plus 0, 4x power 3. So that's it. We found the derivative of x power 4. And let's also find the derivative of x power of 1, as well as of 1. Okay, so we don't actually need to use first principle for this. We can use something called common sense. If we draw the graph of f of x equals to x, we get this very familiar graph. Now the gradient of this graph at every point along it is going to be 1. That's because the curve is a linear curve, it has a constant gradient, and we know that the rise of a run is 1 because y is increasing at the same rate as x is. So we can say that f dash of x, the gradient function, is just 1 because the gradient is 1 everywhere. And for f of x equals 1, we know that that is just y equals 1, that is a straight line here. And what is the derivative of that? The derivative of that is going to be 0 because the gradient at every single point is 0. It's a flat line. So there is no rise, it's only run. So the derivative is going to be 0. So we can actually make sort of a table of what we've found so far with our derivatives of common functions. Alright, let's have f of x up here and f dash of x down here. We have, so far we found 1, x cubed, x to the power 3, x to the power 4. And their derivatives being 0, 1, 2x, 3x squared, and 4x cubed. Now, if you're observant enough, you may find a pattern here. And that pattern is from f of x to f dash of x, what we can say is that the power comes down and you subtract 1 from the power. I should probably change my pen for this. See? So the 3 here comes down here, becomes a factor, and you subtract 1 for it, so it becomes 2. Same here. The 4 comes down here and subtract 1, and the power becomes 3. Now, we can establish a general rule for this called the power rule. So this obviously isn't a very formal proof. Actual proof is normally done with mathematical induction and applying knowledge of the binomial theorem, which we currently don't really have yet. So this is probably all we can do for now. So our general rule is if f of x equals x power of n, we can say that f dash of x is equal to n x power of n minus 1. And that's literally what I just said before. Bring down the power as a factor. So I might write this in words. Bring down the power as a factor. Then subtract 1 from the power. This is our power rule. Important. So now that we've established this very useful formula, let's talk about a few more concepts that we need to know about differentiation. So in differentiation, other than tangent, there's also something called the normal. So what is a normal? If we have a function, let's say like a parabola, and there's a point P here. The tangent to the curve is going to look like this. Touches it just at that one point. What the normal is that it's a line that also goes through P, but is perpendicular to the tangent at P. So basically, that's a bit off. Hold on. This is a straight line, and that's 90 degrees. It is perpendicular. And remember, perpendicular gradients multiply together to produce -1. So if this gradient is m, and the gradient of this is m1 for the normal, m times m1 is equal to -1. Or you can think like the gradient of the tangent, or the gradient of the normal is equal to -1 over m. So you flip the gradient of the tangent and take the negative. So the negative reciprocal of the gradient of the tangent. And one other concept is the angle of inclination. So I'm going to keep using this graph. What the angle of inclination is, I just need to stretch this tangent out a bit more. Okay. What the angle of inclination is basically the angle that the tangent makes with the x-axis, or how steep the tangent is. It's another way of describing it, because we can measure the angle that it produces with the x-axis. And how this is done is that tan theta is just equal to the gradient. Why? Because what we can do is we'll look at it this way. Tan theta is equal to the opposite over the adjacent, which also happens to be how you find the gradient. So we can basically express the steepness of this gradient as an angle, and that's the angle of inclination. So let's go over some sample questions now using these new ideas. So 1, find the gradient of the tangent and the equation of the normal of f of x equals x cubed plus 5x squared minus 4 when x equals 3. Next. Okay, so what we first do is we're finding the gradient, and that usually involves finding the derivative. We start with f of x, equals x cubed plus 5x squared minus 4. And we use our newfound power rule to quickly do this instead of through first principles, which would take forever. I'm not even sure if we could do it properly. So what we do is, to each of the terms, I'm going to do this in red. First, take down the power. The 3 comes down and we have 3x. And remember, subtract 1 from the power. So we have 3 minus 1. Plus, we bring down the power, which is the 2. Since there's already a factor here, we just multiply it with that 5. And x, and the power, subtract 1. For the last term is a constant, and what we can think is basically every constant, the derivative of that constant is 0. Why? There's 2 ways to think about this. We can express it as negative 4x power 0, and if we take the derivative of that, we can see the 0 will come down, and basically we know that the 0 will multiply with that, and basically it just makes it 0, because 0 multiplied with anything is just 0. Or we can just think about it as it's y equals negative 4, and that's still a straight line, a horizontal straight line, and the gradient of that is still going to be 0, regardless of what that number is. If it's a constant, the gradient and the derivative is just 0. So now let's simplify that, and we can see this is much easier than having to find the derivative using first principles. So left with 3x squared plus 10x. Now we need to find the gradient of the tangent at x equals 3. So we sub in x equals 3. So we have f dash of 3 equals 3 squared plus 10 outside of 3. Which, if we expand that, we should get 27 plus 30, which is equal to 57. So the gradient of tangent at x equals 3 is 57. Now we need to find the normal. So how do we find the normal again? We take the reciprocal of the gradient of the tangent, gradient of the normal. We take the reciprocal of the gradient of the tangent, and we take the negative of that. So m1 equals, or we can say m normal. So m is how you would normally write gradient, is negative 1 on 57. And if we want to find the equation of the normal, we should use the gradient point form. So what is that? y minus y1 equals m outside x minus x1, where x1 and y1 is a known point. We only know one point though, which is x equals 3. To find the associated y point, we need to actually sub it into the original function. So to find y1, we need to do y1 for when x equals 3 is equal to f of 3, which is equal to 3 to the power of 3 plus 5, 3 squared minus 4. We're using this original function we had up here. And so we can find that y1 is in fact equal to 27 plus 45 minus 4, which, with a bit of mental maths, should come out to around 68. Okay, so now we can use our gradient point form formula to find this gradient of the normal. The equation of the normal. So y minus 68 equals to negative 1 of 57 outside of x minus 3. This is quite messy. So let's just put it in y equals mx plus b form. What we have is y equals to negative 1 on 57x plus 3 on 57 plus 68. And that is some complicated fraction that I cannot be bothered to work out. So I don't have a calculator with me right now. So unfortunately, I'm just going to leave it as this. This obviously you would have to simplify into a mixed fraction. I'm just going to leave it as a smiley face. But yeah, that's basically the process of finding the equation of the normal. Obviously, you would do the same if you were asked to find the equation of the tangent, but normal is even harder because you have to consider the reciprocal of the tangent. So that's why I chose that question. Let's go to the next question, which is find the derivative of f of x equals to root x plus 3 on x cubed minus 4. Okay, this is interesting. We've only dealt with whole number and positive integers as powers. But basically, the power rule extends to everything. All we have to do is just write these as indices. So how is that done? We know that root x is the same as x power of a half. We know that 3 on x cubed is the same as 3x power of negative 3. And we know that minus 4 is just minus 4. So now that we have it in this index form, we can use our power rule. And let's do it on each one of these in turn. Half comes down, so we'll have half x, and subtract 1 from this, and subtracting 1 from a half is going to give you negative half. Plus, the minus 3 comes down, so you get negative 3 times 3, x, and then subtract 1 from this negative 3, you get negative 4. And then the negative 4, we know, just becomes 0. So that's our derivative, and let's simplify. So what we have is x power of negative half is just going to be 1 over 2 times 1 over x power of half, because the negative indice means it's going to be flipped and the negative disappears. And then negative 3 times 3 will be negative 9, so we have minus 9 and times 1 over x power of 4. So we'll simplify that once again. And changing the x to the power of half back to index form, we get 2 root x minus 9 over x power of 4. So that's our derivative. It's pretty simple. It's just recognizing that power rule also applies to fractional indices. You just have to get it in that form that you can apply the power rule. Okay, this last question, I'm gonna let you guys also have a go as I do it. So I'm gonna write down the first. It's a multi-part question. So I'm gonna write down the first part. Pause. You can pause the video, have a go, and see how you go. So find the derivative of f of x equals 2x squared plus ax, where a is a constant. So pause the video, have a go. Okay, hopefully this wasn't too hard. Shouldn't be at this point, but so applying the power rule, the 2 moves down. So this 2 comes down here, and we subtract 1 from the 2. So our first term is 2 times 2, x power of 1, and the x is just x power of 1, so the 1 comes down, and we're just left with a, and the 1, you subtract 1 from it, so you're left with a, x power 0. X power 0, anything to the power 0 is just 1, so what we have is 4x plus a. And that's our derivative. Okay, the second part of this question, so part II, the tangent, for the following questions, it's going to be find the value of a when the tangent at the origin has a gradient of 9. Pause the video, have a go, and hopefully that was enough time. So basically what we need to find here is the gradient of the tangent, and basically that's just the derivative. So we basically need to find f when f dash of x, which is our gradient function, is equal to 9, and we know it's at the origin, so that's x equals 0. So what we're basically trying to find is f dash of 0 equals to 9. And now f dash of 0 is 4 times 0 plus a equals to 9. So we just have a equals to 9, and that's the value of a. So it's pretty simple. It's just interpreting the question. It's a slightly different approach because you're finding an unknown constant given the point and given the gradient at that point. So the third part, once again continuing this question of finding the value of a, find the value of a when the tangent at the point x equals 3 has an angle of inclination of 45 degrees. Once again, pause the video, have a go. Okay, hopefully you got an answer. This is a very similar approach to the last question. We know the tangent is at the point x equals 3. So the tangent at the point x equals 3 should be equal to f dash of 3. Because our f dash of x is our gradient function. We plug in a value and that will tell us the gradient at that point. So an angle of inclination of 45 degrees, what does that actually mean? Basically, that just means a gradient of 1. If you remember the angle of inclination, so if this is 45, our gradient here is m equals 1. So our gradient is 1, or we can just write equals tan 45 equals to 1. Our f dash of 3, plugging it back into what we had before, is 4 times 3 plus a equals to 1. So 12 plus a equals to 1, a equals negative 11. So the fourth part of the question is, find the value of a when the tangent at the non-zero x-intercept has gradient 7. So what we need to do here is sort of go back a step and look at our original function. f of x equals to 2x squared plus ax. So basically, we can factorize this to find the intercepts and make it x outside of 2x plus a. To find the intercepts, we let that equal 0, and we can see that the intercepts are at x equals 0 and 2x plus a equals 0. So if we solve for x, there is the other intercept is x equals negative a on 2. So here are our two intercepts, and we're interested in the non-zero x-intercept. So that'll be this one. So it's saying the tangent at the non-zero x-intercept has gradient 7. That means f dash of negative a on 2 equals to 7, because we're subbing in that point into our gradient formula, and that point should be equal to 7. So we look at our derivative is 4x plus a, so we sub it into that, 4 outside a on 2 plus a equals 7, and we get negative 2a plus a equals 7, and negative a equals 7, a equals negative 7. So that's the value of a when the tangent of the non-zero x-intercept has gradient 7. So that's it for the lesson. I'm going to propose some homework problems. Solutions will be posted in the next video. So the following are a bit of a warm-up because finding derivatives is done through a lot of practice. You have to get used to the techniques. You have to get used to looking at questions. So here are just some warm-up questions. So find the derivative of f of x equals 3x power 5 minus 4x squared plus 2x plus 1. F of x equals to, this is 1, 2, 4x squared outside our root, 3x plus 1, and so that's going over 3 and x, this whole thing square rooted, and f of x equals to 4a squared x cubed plus bx minus c to the power 4, a, b, c constant. and then find the equation of the tangent and normal of the curve f of x equals 7x to the power 4 minus 8x to the power negative 6 plus 2x plus 2 at x equals 1. Part C, show that the tangents at the x-intercepts of f of x equals x squared plus 4x plus 31 have opposite gradients. Explain why this is the case through finding the turning point of the parabola. Okay, that's it for this video. See you guys next time.